This is Chemistry for Grade 9, produced by Tigray Education Bureau, transmitted by Dimtsi Weyane Tigray National and FM radio satellites and social media, and also FM Maqala 104.4.
Hello students, this is Chemistry for Grade 9, presented by Guish Tasfai. Welcome to second week lesson on 4.8 rate of chemical reactions and chemical equilibrium. Students, last time you learned about stoichiometry and oxidation reduction reactions. Stoichiometry is the quantitative relationship between reactants and products in a balanced chemical equations. Oxidation reduction reactions is a reaction that involves transfer of electrons. Let us begin our lesson now. Open your textbook at page 145. 4.8.1 Reaction rate. Students, define what a reaction rate means. Hello again, students. The rate of a reaction is the rate at which reactants are converted to products. And there are different methods in which the rate of a reaction can be monitored. Those could include change of a color, volume of gas involved, amount of precipitate formed, loss or gain of mass. Therefore, reaction rate of a chemical reaction is defined as the change in concentration of a reactant or a product per unit time. That is, a rate of reaction is equal to change in concentration divided by change in time. Preconditions for a chemical reactions. Students, list and explain the preconditions for a chemical reactions to take occur. Well, the preconditions for a chemical reactions to take occur are collision between the reactants, activation energy, and proper orientations. Now let us discuss each preconditions. The first precondition for a reaction to take occur is collision between the reactants. Collision is the direct contact of reacting substance with each other. However, all collisions between molecules are not necessarily effective in bringing a reaction. The second preconditions for a reaction to take occur is the activation energy. Of course, activation energy is the minimum or sufficient amount of energy required to initiate a chemical reaction, so that if the collisions between the reactant molecules do not have sufficient energy, no reaction will occur. Since for the reaction to take place, collision must always occur with sufficient energy to break the bonds in the reactants and form new bonds in the products. The third precondition for a reaction to take occur is the proper orientation. Because collision of molecules with sufficient energy will not bring a reaction. if the reactants lack proper orientations. Therefore, reactants must collide for a reaction to take occur in a proper way or effective collision. Factors affecting the rate of chemical reactions. Students, list factors that affect rate of chemical reaction. Good. The factors that affect a chemical reactions are 1. Nature of the reactant, 2. Temperature, 3. Concentration of the reactants, 4. Pressure or volume, 5. Surface area, and 6. Use of a catalyst. Students, those factors are explained in terms of collision theory. The collision theory assumes that the rate of a reaction depends on the frequency or number of collisions of particles, and those factors which affect the frequency of collisions will also affect the rate of a reaction. Now, let us explain each factors. 1. Nature of the reactant. Let us consider the following reactions. Magnesium plus 2 mole of HCl, it gives us magnesium chloride plus hydrogen gas. And iron plus 2 mole of HCl, it gives us iron chloride plus hydrogen gas. The reaction between magnesium and HCl is at a fastest rate because magnesium is reactive reactant than iron, whereas the reaction between iron and HCl is at a slow rate because iron is less reactive reactant than magnesium. 2. Temperature. As increase in temperature increases the kinetic energy of the reacting particles, so there is greater chance of collisions being effective and results in an increase in the rate of reactions. 3. Concentration. As increase in the concentration of the reactants provides more reacting species for collisions and results in an increase in the rate of reaction. 4. Pressure or volume. As increase in the pressure of the gaseous reactants provides more reacting species for collisions and results in an increase in the rate of reactions. 5. Surface area. Increasing the surface area of a solid reactant increases the chance of collisions with the other reactants. That is, the higher the surface area of reactants, the faster is the rate of the reaction. This is because more contact results in more collisions between each small particles of reactants. 6. Use of a catalyst. A catalyst is a substance that speeds up a reaction by lowering activation energy without itself being consumed. 4.8.2 Chemical equilibrium. Students, define the terms irreversible reaction and reversible reaction. Okay, students, chemical reactions can be classified into two: irreversible reaction and reversible reaction. A reversible reaction, it is a one-way reaction that proceeds from left to right. It proceeds to completion. Reactants are quantitatively converted into products, and the amount of limiting reactant that remains is negligible. Reversible reaction. It is a reaction that proceeds into two directions. It does not go to completion. The reaction that proceeds from left to right is called forward reaction, and the reaction that proceeds from right to left is termed as backward or reverse reaction. Chemical equilibrium is the state of a chemical reaction in which the rate of forward and reverse reaction is equal, and the concentration of all reactants and products remain constant with time. Therefore, chemical equilibrium is a dynamic process. Chemical equilibrium constant expression. Students, state the law of mass action and write the expression for equilibrium constant of a reversible reaction. Nice. The law of mass action or law of concentration action states that for a reversible reaction at equilibrium at a given temperature, the equilibrium constant is equal to the amount of products divided by that of reactants, each raised to the power of its coefficients in the balanced equation. Let me consider a general reaction. Small a as a coefficient of capital A plus small b as a coefficient of capital B at equilibrium with small c as a coefficient of capital C plus small d as a coefficient of capital D. According to mass action, rate of forward reaction, RF, is directly proportional with the concentration of A to the power of A, concentration of B to the power of B. Then rate of forward reaction is equal to rate constant for the forward reaction, Kf, times the concentration of A to the power of A, the concentration of B to the power of B. Also, rate of backward, Rb, is directly proportional with concentration of C to the power of C, concentration of D to the power of D. Then rate of backward is equal to rate of constant for the backward reaction, Kb, times concentration of C, the power of C, times concentration of D to the power of D. Since at equilibrium, rate of forward reaction is equal to rate of backward reaction, then Kf times concentration of A, the power of A, times concentration of B to the power of B is equal to Kb times the concentration of C to the power of C, times the concentration of D to the power of D. After rearranging the equation, Kf divided by Kb is equal to the concentration of C to the power of C times concentration of D to the power of D divided by concentration of A to the power of A times concentration of B to the power of B. that is concentration of product over concentration of reactant. The ratio of Kf to Kb is called equilibrium constant, KEQ. KEQ is equal to Kc if the amount of products and reactants expressed in molarity, and KEQ is equal to Kp if the amount of products and reactants expressed in partial pressure. Therefore, Kc is equal to concentration of C to the power of C times concentration of D to the power of D divided by concentration of A to the power of A, concentration of B to the power of B. And Kp is equal to partial pressure of C to the power of C times partial pressure of D to the power of D divided by partial pressure of A to the power of A times partial pressure of B to the power of B. This Kp is applied only for gaseous substances. Remember that when we write equilibrium constant expression, pure solid and liquids are not included in equilibrium constant expression because their amount is constant. Example: given the reaction A plus B at equilibrium with 2C. For this equilibrium reaction, Kc is equal to 100. The concentration of A is equal to 0.25 molarity. The concentration of B is equal to 1 molarity. Then find the concentration of C at equilibrium. Solution: Kc is equal to the concentration of C to the power of 2 divided by concentration of A times by concentration of B. Then recross this Kc times the concentration of A times the concentration of B is equal to the concentration of C square. The concentration of C is equal to the root of Kc times the concentration of A times the concentration of B. The concentration of C is equal to the root of 100 times 0.25 molarity times 1 molarity. Multiply and take the root of, then the concentration of C is equal to 5 molarity. Do it again, this example, using the formula written on your textbook. Let us summarize the main points of the lesson. Rate of reaction is the change in concentration of reactants or products with time. Reversible reactions take place in both the forward and backward directions. Irreversible reactions proceed only in the forward direction. Chemical equilibrium is the state of a chemical reaction in which the rate of forward and reverse reaction is equal. Students, this is all about today's lesson. Next week, you will learn about the factors affecting the position of equilibrium. Until next time, goodbye.